Hello everyone. In this submodule, we will understand how can an integrated water quality and sediment management plan can be devised and what are the various specifics that needs to be understood. Now, when we talk about the water quality monitoring, there are various systems that are there in place. So one can be the automated water quality monitoring systems. So has been placed by the Central Pollution Control Board in India, which has set up a network of real-time water quality monitoring stations across major rivers and water bodies. These use sensors to measure the parameters like pH, dissolved oxygen, turbidity, and other electrical conductivity, which transmit data in real time. There can also be some remote sensing and GIS, for example, used by the Indian Space Research Organization (ISRO), which would use remote sensing satellite like Cartosat and resource set to monitor large water bodies, track changes in the water quality, and manage resources efficiently. The GIS are also used to create detailed maps and models of water quality, which would integrate the data from various sources for comprehensive analysis. Then there is the Internet of Things technology to deploy the smart sensors that provide continuous real-time data on various quality parameters. These often interact with cloud-based analytics platforms that process and analyze data, providing actionable insights and alerts for water quality management. There are various laboratory-based analytical techniques as well. There might be the high-performance liquid chromatography or mass spectrometry methods that can be employed to identify and measure the trace levels of various compounds like heavy metals, organic compounds, and other pollutants as well. Now, this water quality monitoring can, with the advent of the Internet of Technology or the 5G, it can be connected with the cloud computing as well in order to collect the real-time data with a number of sensors at a particular watershed, and then it can be shared with the various stakeholders or the various organizations that are required. So we can have something like an acoustic transmitter tag with a water conductivity and temperature sensor, which would be able to quantify the different water qualities. This tag would be based on a ultra low power mixed signal electronic design similar to an acoustic tag platform. Then we could have some sensor integration, onboard data processing and storage capacity. So a proper data infrastructure can be built up in order to collect the data, store data, analyze it, and then share the results with the various organizations in real time. There are also various wireless sensor networks that have started gaining attention as the communication and techniques have been improved. These have proved to be very efficient in wirelessly monitoring the environmental data and the ability to acquire and process the data from widely distributed sampling points using low power communication networks. Now, this assists various decision makers to capture data from various remote sensing locations in a timely fashion. So in such cases, it is not only the sensed parameter that is needed, but also the ID of the sensor is also collected, which is then used in a silicon-based integrated circuit, which is a very established technology. Furthermore, there are various silicon-based tags as well, which endure environmental conditions like high temperature, pressure, humidity, and radiation. And various chipless technology have also been developed, like the surface acoustic wave sensor tags, which can understand what are the various water environments under harsh environmental conditions as well, and can reflect or backscatter at power level emitted from the reader. So these sensor networks have also been developed to monitor the water quality. Now, the water quality monitoring in river often focuses on the concentration of sediments and nutrients, various constituents that can smother the biota and cause the eutrophication. However, there are physical and economic constraints of manual sampling, which prohibits the data collection and the frequency required to adequately capture the data variation in the concentrations of the water quality parameters through time. There have various models which have developed to predict the total suspended solids and the nitrogen content based on the high frequency time series of turbidity, conductivity, and river level data from various in situ sensors in the rivers. There can be various generalized linear mixed effects models with continuous first order correlation structures to water quality data collected by manual sampling to predict the total suspended solids and the nitrogen contents as well. Turbidity is one of the most useful data factor that is used. Then there are various surrogate based models as well to predict sediments and nutrients to better incorporate the temporal variations in the data collection parameters. So a wide range of modeling techniques have been used to describe the relationship between the sediment and the nutrient concentration and other water quality parameters. For example, there have been the artificial neural networks that have been used to predict nitrate from multiple parameters like the turbidity, the nitrogen content and all. Then there have been various regression models to quantify the relationship between the various water quality parameters and the suspended solids as well. We have linear regression models, serial correlation models have been developed in order to find a unique relationship between the water quality and the various chemical composition of the water parameters that are there. Now, when we talk about the models that are there, we have models for the local field scale applications, which include the event-based time step models, which are appropriate from short-term and management of water quality monitoring. Now, these are generally too data intensive and again are based on the localized conditions only. There are models like the sediment model and the N-spect models, which have been used in extensive application to estimate the end of river loads of sediment and nutrients and to target the catchment management to minimize the impact of this sediment runoff and the water quality systems. Now both estimate the long-term pollutant supply in the sediment loads and are also considered good in terms of the model scope, data requirements and performance as well. So models have been developed, but when we talk about the tropical conditions, we have to look into what kind of model will fit our particular case study that we are looking into, because again the sediment influx varies in the Indian subcontinent. Another model is the graded water quality model that is there, which is an open source model. And so basically there have been efforts to develop a next generation global hydroeconomic modeling framework that can explore the economic trade-off among the different water quality options, which encompass both water infrastructure, the management of water demand, the water resources, and the water quality. All the data can be integrated into form and water quality model, which again includes the sediment transport and the salinity data. With the rapid increase in the volume of data on the aquatic environment, machine learning has also become an important tool for data analysis, classification, and prediction. Now, unlike traditional models used in water-related research, data-driven models based on machine learning can efficiently solve more complex nonlinear problems. In the water environment, research models and conclusions can be derived from machine learning, and these have applications in the fields of construction, water monitoring, simulation, evaluation, and optimization of the water treatment and management systems. Additionally, these ML-based models can provide solutions for water pollution control, water quality improvement, and watershed ecosystem security management. Machine learning algorithms have been applied to evaluate the water quality in different water environments such as the surface water, groundwater, drinking water, sewage, and seawater. So this integration of the machine learning can also aid in having a good large scale water quality model. Now, when we talk about such models, we would require key data sources and then understand what is the processing and application for each of the step of the particular ML based model, which would integrate what data is applicable, what is the limitation, and what kind of adjustment are to be made when we talk about the tropical condition. So when we talk about what data can be required, we have various options like the catchment and stream network delineation for understanding how the watershed behaves. There is the runoff and flow calculations for the sediment load calculation. What are the various dissolved pollutants and nutrients that are there? Then the hill slope and the gully erosion to track the amount of sediment influx from the erosion that is there. Then what are the various particulate nutrients present in the water that we are focusing into? Deposition and loss of sediment and nutrient over time in order to have a future timescale predictability. And then the sediment delivery ratio into the particular water body that we are focused on. For developing any sediment related water quality management system, we can look into the case study of the Yellow River in China as well. Now, this Yellow River is well known for its high sediment concentration and has been widely concerned and studied area. Now, due to the natural factors in the river basin, it has a large amount of non-point source pollutant, and there have been water quality problems as well. Now, many researchers have assessed the water quality in parts of the Yellow River using various parameters, but these have low efficiency and high cost. Now, based on the high sediment load, the water and the sediments in the entire mainstream of the Yellow River have been thought as a multi-level reservoir river continuum and were comprehensively considered to develop a water quality index or a water quality index model. A total of 26 parameters were measured to water quality in the Yellow River, and the objectives were to assess the water quality status of the Yellow River using this WQI, the water quality index method, and then to identify what are the key parameters which affect the water quality and establish a model based on those parameters. Now, when we talk about the what the project achieved, it showed that the impact of the sediment load of water quality in the river is clearly critical, and it showed that in low sediment rivers, the total suspended storage is usually used one of the parameters, can be used as one of the parameters in the model that they have developed. So we can look into the case how they have collected the various parameters required for the model, how they have led to the ground and the field validation of the model. And similarly, if we can develop something for our own systems, it can be of great use for any future. Thus, we would require an integrated water quality management plan, which would include the sediment management. So this would include various components. So one would be the assessment and monitoring of the water quality, the baseline data collection, identification of the water bodies at risk, sediment quality assessment, understanding the sediment sources and hotspots that are there. Then watershed management, which would include the watershed delineation, mapping of the watershed area, land use planning, what are the best management practices for agriculture, urban and industrial areas. Then the sediment management techniques would involve the sediment traps and basins, installation of the sediment detention structures, regular maintenance and the sediment removal, the dredging and sediment removal, controlled dredging operations to maintain the water quality that is there. This would also involve the public participation and stakeholder engagement, as the communities are also getting affected due to the water quality. Stakeholder collaboration would be required, formation of watershed councils or advisory groups, and regular stakeholder meetings and workshops would be required. Then we would require a policy and a regulatory framework which would have regulation compliance, adherence to the local, regional, and national water quality standards, incentive programs, and then financial incentives for adopting the best management practices that are there. We would like to have an integrated data management and decision support system which would have a centralized database for water and sediment quality data. We could use the GIS for data visualization. There can be modeling and analysis, hydrological and sediment transport modeling, scenario analysis, and predictive modeling as well. And finally, the evaluation and adaptive management techniques can be used to evaluate the performance, the regular assessment of the plan effectiveness, feedback mechanisms are there, stakeholder feedback and periodic reviews, and then incorporation of the lessons learned into the management plan in order to have flexibility to adjust the strategies which are based on the monitoring results. Thus, how the UDA will help by integrating all of this data with the marine spatial planning. This marine spatial planning will help us make informed decisions that when we talk about the water quality management, we would require different kind of data that needs to be shared between the various stakeholders. Active stakeholder engagement needs to be there. For this, we would require the proper sensitization of the specific stakeholders that we want to target. And again, without any data collection or data analysis, we can't move forward. So for that, how can we integrate the Internet of Things, the cloud computing technology? UDA talks about how the digital transformation can aid. We can use the digital transformation, skilling of workforce to the AI techniques can be used in order to have a holistic view of the water quality management and how the sediments are impacting the water quality. So with this, I'll end the discussion here. Thank you.